We have an important question as a fourth question. We need to find out, we have a disk of uniform charge density sigma. This is a disk of circular disk of uniform charge density sigma. We need to find out the electric field at a distance x on the axis, the electric field at this point due to this disk of charge density sigma, uniform charge density sigma. So for solving this, the first thing you should think of is how to find out the electric field. We have to find out the electric field due to every charged particle over here and then add them vectorially. Now instead of taking every particle, it becomes very difficult if we do like that. So instead we like to take a small elements of whose electric field we already know on the axis and then integrate them. So by intuition, the best small element we can find out here is that a ring. I'll draw the diagram again. This is a disk. We need to find out the electric field at a distance x. This is perpendicular to the disk. The disk is like this and this axis is perpendicular to the disk. We take this ring over here at a distance r. The radius of the disk is given to be equal to r, capital R. We take a ring of thickness dr at a distance, this thickness is dr. Now we already know the electric field due to a ring on its axis. If you do not know, you should remember the formula. The electric field due to a ring on its axis is kqx upon r square plus x square raised to the power 3 by 2. This is the electric field due to a ring of charge q on the axis at a distance x from the center of the ring, perpendicular from the plane of the ring. So using this, we write down the electric field dE, small electric field due to the small ring at this point, to be equal to k into the charge of the ring. The charge of the ring can be written as sigma into area of the ring. Area of the ring now can be written as 2 pi r into dr. This is a direct way to write it. You can imagine this as 2 pi r is the circumference of the ring into dr. That becomes the area of the ring. If you cannot understand like that, you can also do it like the area of the ring as pi of r plus dr whole square minus pi r square. You will get the same answer. Another way to imagine it is 2 pi r is the circumference into dr. It gives you the surface area of the ring. Therefore we can write this as sigma into 2 pi r dr k q into x upon r square plus x square raised to the power 3 by 2. So this is the small electric field in this direction due to this ring. Now due to all the rings, the electric field will be in this direction. So we can integrate them because we can integrate only scalar quantities. So we will integrate all the vectors in this quantity in this direction. We will integrate their magnitudes in a scalar fashion. Therefore we get the total electric field to be equal to integration of k into sigma 2 pi r dr into x upon r square plus x square raised to the power 3 by 2. And since the integration is in terms of r goes from 0 to capital R, so that we cover all the rings. Now we are seeing here that this integration is looking pretty difficult in terms of r. So in these type of questions, it is always preferable to solve this question in terms of angles, that is theta. Now this ring has a unique property that it subtends an angle of theta at this point. Therefore we can write tan theta is equal to r upon x, rather r is equal to x tan theta. So dr becomes equal to x sec square theta d theta. We can substitute everything over here. The limits of integration will also change to give us E is equal to integration. The angle initially will be 0 and finally will be equal to tan inverse of capital R upon X. Now mind you, X is a constant over here. It is not a variable. This is a constant, this is not a variable. R, small r is a variable, right? So here K sigma 2 pi into X into R dr. R dr becomes equal to X square into tan theta sec square theta d theta upon R is equal to X tan theta and dr is equal to X sec square theta d theta upon R square plus X square raised to the power 3 by 2. So R square becomes equal to X square tan square theta. So X square comes common here. So X square raised to the power 3 by 2 becomes X cube. 1 plus tan square theta becomes equal to sec square theta. Sec square theta raised to the power 3 by 2 becomes equal to sec cube theta. So we cancel sec square theta and a sec theta remains here. Cancelling this, we get sin theta. This x cube gets cancelled. So the beauty of the question lies here that to make the substitution tan theta is equal to r by x. These type of integrations are always easy when you solve in terms of angles. So what we get here is that E is equal to 2 pi sigma k integration sin theta d theta. Integration goes from 0 to tan inverse r upon x, but we find here that integration of sin theta will be minus cos theta. So it is preferable if we write this in terms of cos theta. Therefore tan theta, cos theta can be written as, finally the final value of cos theta for this angle, this will be theta naught. Let me write this as theta naught or theta final. Cos theta final will be equal to x upon root over r square plus x square. Therefore theta final can be written equal to cos inverse x upon root over r square plus x square. 1 second. Theta final is equal to cos inverse x upon root over r square plus x square. Let me substitute that value here. This is equal to cos inverse x upon root over r square plus x square. Now we can easily solve this. E becomes equal to 2 pi sigma k minus of cos theta 0 to cos inverse x upon root over r square plus x square. So we get from here E is equal to 2 pi sigma k into 1 minus x upon root over r square plus x square. K can be written to be equal to 1 upon 4 pi epsilon naught. So we get the final answer for the electric field to be equal to sigma upon 2 epsilon 0 1 minus x upon root over r square plus x square, and the direction of this electric field is vertically upwards. So final answer for the electric field comes out to be sigma upon 2 epsilon 0 into 1 minus x upon root over r square plus x square.